Chapter 8 Engineering Mechanics Dynamics. Mark Frisna, Professional Engineer Introduction. Discipline is to study with the motion force given them with a motion morning session with a fundamental exam, typically contained with a 9 to 15 exam with problems related with the various dynamic topics. The afternoon session of General Engineering Mechanical Discipline examines with approximately 10% of the total question of the area of the dynamic system, following with a review models or with the intent of the render reader with reinforce his or her knowledge of the relevant dynamic principle and problem-solving techniques that are likely to appear on the fundamental exam. Kinematics of particles, kinetics of particles, work and energy, rigid body motion, and plane vibration summary. 8.1. Kinematics of particles. The study of the patterns of motion with respect to the section focuses on describing the two-dimensional plane motion, three-dimensional space motion, and employing rectangular coordinates, tangential, normal coordinates, and radial transverse component of the effect forces on the motion outside of the domain of kinematics. The most important parameter of particle kinematics are the vector of the represent position, velocity, and acceleration. RT is the instantaneous time dependent with a position vector particle with a defined reference origin space. Instantaneous velocity is defined by the time rate of change position vector is represented by the relationship instantaneous velocity is equal to dx over dt, distance where v is the typical unit with a mass over seconds or foots or seconds. Instantaneous acceleration represented with the symbol at is defined as the rate of change of the velocity of the vector e over the governing equation acceleration. Instantaneous acceleration over the distance of the vector times the time over the distance of the time equal to the distance squared times the instantaneous time dependent position vector over distance time squared. Instantaneous velocity, the acceleration successive with the derivative of the position of the equation. Generally, the units acceleration are meters over second squared or foots over second squared. Instantaneous velocity would be equal to dxt over dt, dyt over dt, and ij and k, or x I plus y j plus z k. Acceleration vector is equal to x y yj dk. Rectilinear motion. Rectilinear motion is straight line motion space within the plane with a short motion restricted to a single line action space or plane. Particular motion confined with the x-axis horizontal direction. Example of rectilinear motion. This is the initial position velocity denoted by the xo and v0 vo. Respective general equations, conditions variable velocity for the time and acceleration are given with a motion t0 to t. Instantaneous position xt to x0 equal the derivative t0 vt d distance time. Instantaneous velocity time v0 equal the derivative t0 acceleration time times distance and time. Uniform velocity occurs when the uniform velocity, or v constant, is straight linear motion, which requires a to 0. Instantaneous position equals x0 times velocity equal to t minus t0. Particle displacement x resultant defined in depth of change with the resultant x is equal to x instantaneous position times x0 times the derivative t0 instantaneous velocity with the distance and time. In fundamental exam problem, the velocity versus the time graph provided with the displacement can readily be obtained calculating the area of the graph during the specified time interval with the capability. Especially useful velocity graph contains several different velocity instantaneous velocity functions. Uniform acceleration a is equal to constant rectangular motion velocity linear function. And the initial conditions of x0 and v0 are given with the key equations. Instantaneous position rectangular is equal to xo plus velocity with a t 0t plus at squared over 2, or to is equals 0 for times 0. Velocity of time is equal to velocity 0 at acceleration times velocity squared is equal to velocity 0 squared at 2 times acceleration times x minus xo. Plane circular motion. Plane circular motion requires that the particular transverse path of the plane with the radius curvature r is constant with respect to reference origin c, with the central curvature of the path of the tangential normal accordance to u with the profile of circular type of motion. Reference figure 8.1. Important to recall tangential direction along the line of action. Velocity of typical positive motion results in an increased angle. Counterclockwise direction. Normal direction directed positively from the particle toward the center of the curvature. The normal direction always points inward toward the center of the curvature. For circular motion governing equations, angular velocity, angular acceleration, tangential velocity, tangential acceleration, normal acceleration, total acceleration, scalar arc length, distance along the curve. Or radial transverse components of plane motion. Radial transverse covariant linear motion upon radius curved particular plane path and plane usually varies in time, except with the unique case of circular motion. Figure 8.2. Radial direction along the line of action reference original particle. The radial distance at time is denoted by the radius times time, and the positive of the radial direction is directed away from the origin. Transverse direction is always perpendicular to the radial direction. The positive transverse direction tends to cover the increased angle position vector in counterclockwise sense as shown. Spiral motion, elliptical motion, a classic example of plane motion as best modified radial transverse components. Shows radial and transverse. Radial transverse components effectively two-dimensional vector versions of cylindrical coordinates. Fundamental engineering exam problems related to radial and transverse components usually provide equations of radial distance, RT, angular measurement, and a typical problem often asks for the computation velocity and or acceleration magnitudes radial transverse components governing equation radial transverse planes, and as shown. Radial velocity equal to the radius equal to the distance of the radius times time over distance time. Transverse velocity velocity is equal to the radius times 0. Total speed radial 0. Velocity total speed is equal to the square root of velocity radius squared times velocity angle 0 squared. Radial acceleration radius is equal to the radius, and I don't know what the two dots stand for, but minus radius angle squared. Transverse acceleration angle equal to radius time plus 2 times the radius angle. Total acceleration square root of angle radius squared angle 0 angle 0 squared. Relative plane motion. Relative plane of one object with respect to another plane will determine the taking of the vector of the individual absolute quantity of the two objects measured with respect to the common difference reference datum. Specifically relative to the velocity of the object t is desired, the subject respect is viewed as this object s as if the vector s and vector t, or velocity s and velocity 2 instantaneous velocity vectors s and t respectively. The note specifically order vector subtraction following equation. Relative velocity of t with respect to s is velocity of t over s equal to velocity of t minus s. Bear in mind the solution of vector subtraction is often found setting up the vector triangle. Calculating magnitude direction desired relative with the velocity of the use of the low cosine loss of sins. Relative position relative with acceleration requests in fundamental engineering exam problem. First determine about absolute position vectors, acceleration vectors as specified at the time when using solution technique described above with relative velocity. Dependent motion. When the position of one particle depends on the position of another particle, other particle with a motion that is so said to be dependent. Depending motion problems usually involve particle with a connected v with some Pauli arrangement. The main objective is to establish relation between the velocity and acceleration of the connected particle. Following the example, the will does demonstrate how this is done. Shows the example and shows a Pauli system. Alright, projectile motion. Problems involved with the projectile motion quite often represent the dynamics section of the fundamental engineering exam. The typical curvilinear motion usually involves the following condition. Particle trajectory confined to an XY plane. Only gravitational force as immediately after particle initially projected. Resistance aerodynamic forces are neglected. The initial evaluation of y angle the object is given the relative datum. Other initial conditions such as velocity angle and projection angle. The velocity makes the horizontal may provided or need to be determined. Figure A3 illustrates initial conditions listed above, but note the object may have two different times the same elevation because of the quadratic equation for y's time given below. Be prepared to solve the maximum horizontal distance range r, and which occurs at y0, as well as the time required for the reach maximum height of ym. Maximum height of the projectile motion occurs in vertical velocity, or vy is 0. And it shows the figure projectile motion equations. Assume that time 0 is 0, x time is equal to velocity 0 cosine angle 0 angle t. Y time is equal to y0 times velocity y0 at time over g time squared over 2, or equal to y0 plus z0 velocity y angle versus y plus z velocity angle sin times angle time minus g times time squared over t. Alright, Vx is the V angle cosine 0 constant. Vy times t is equal to velocity O sin times gt. And Ay and angle y is equal to negative g. Alright, 8.2 kinetic subparticles. Kinetic study with respect to the force of the motion, particle dynamics. Newton's second law of the motion is governed principle of Newton's second law of motion. Newton's second law of the motion, constant mass object of the particle with a logarithm force over the mass of the acceleration. The force and logarithm of force, not external forces acting with the object, typically has unit pounds force as kilogram newtons, and a acceleration vector that must have the same instantaneous direction as the net force. Since numerous fundamental engineering problems in the kinetics are centered over the second law principle, the following general solutions procedure is strongly recommended. Construct an effective three-body diagram, objective being analyzed, that requires identifying with the drawing all external forces known as unknown acting on the mass of their point of application. Select appropriate coordinate system, attach reference x's to the center of gravity of the body. 3. Resolve all known unknown forces components for each axis. We're paying strict attention to the sign convention. Then write the second law of the equation along the established axial directions. 4. Solve the simultaneous component equation for the desired force acceleration, recognizing the two unknowns normally solve in a two-dimensional problem. Note that all conversion errors are often made with the second law of computation involving the mass or weight. Observe the following constants. When using an acceleration log force over the mass, be aware that 50 pounds of foot and 50 pounds of mass is not equal to 1.0 foot second. The universal conversion of 1.0 pound a foot is equal to 32.2 pounds a meter, or pounds of mass foot squared second squared. Should be carefully employed. Avoid miscalculation weight using simple formula weight equals mass times gram. Proper use of conversions given above, also known as gram C or gram C, will prevent errors. Rectilinear motion, straight line motion, probably involved with a fixed mass object with some system of external forces, typically solved with the scalar components version. Newton's second law described above. Rectangular motion, x, y, and z coordinate frame, where object's instantaneous position is defined with the function xt, yt, zt. The governing components of the equation as follows. The logarithm of force x is equal to mass acceleration x equal to mass direction distance squared times x time over distance rate times squared equals mass x. Logarithm fy is equal force y is equal to mass times acceleration y equal to mass y, and force logarithm force z is equal to mass times z. Note that the magnitude of the total net forces acting on object is the logarithm of force is equal to the square root of the logarithm of the force for x, y, and z squared added all together. Then it goes into examples. Solutions. Plane curvular motion. Curvature motion is a plane fixed mass object particle of Newton's second law employed with the help of the fundamental engineering. Although majority of the example of the problem's area relate to a circular arc-type motion described in tangible normal components given in the functional following section, occasional field problems involve the variable radio with the curvature of the best solved with employing radial transverse coordinates. Central force problems such as gravity-driven motion as is category. Non-circular motion forces logarithm force R is equal to mass acceleration R, where radial force is directed toward the wave of the original path. Logarithm F angle force angle equal to mass acceleration angle, valid transverse force in perpendicular radial direction. Use expression angular radial forces angle and transverse forces given on page 204. Tangential normal forces, circular type motion planning involve fixed mass object. Tangential normal forces are involved with a solution variety of fundamental engineering exam. Specific problem categories that often appear include with a cable to tangent object, travel line, the circular path of roller coasters requiring reaction force, central pedal forces, acceleration, tangential forces, circular arc-type motion, log force time, O equals mass angle acceleration time, mass radius acceleration where radius is constant, normal forces for and logarithm of force, normal forces, mass acceleration, normal forces equal to mass velocity squared over radius, resonant forces equal to mass resonant forces squared. No centripetal forces are equivalent to normal forces. Centripetal forces equal to mass velocity squared over resonant forces. Alright, linear motion constant mass particle with the object vector quantity L, which is simply defined as a product with a particle object mass instantaneous vector known as linear motion equal to mass times velocity. Conventional units of the linear motion are pound foot seconds or Newton second. Also called fixed mass object net force acting equal time rating change linear momentum for equation logarithm force is equal to the distance of the linear moment over distance time equal to mass times distance times velocity over the distance of the time. Effectively restates Newton's second law. An important ramification above the equation is that the net forces acting on fixed mass object zero is necessary for the linear motion equal the constant objective velocity remains constant. Clear example of the condition occurs when a puck travels across the horizontal frictionless air table over the constant speed. For the dynamic section fundamental engineering, understanding the linear moment, the concept of the essential solving frequently represented impact impulse momentum problem. See page 2 in the 08 through 209. Conservation of linear momentum for a single particle having constant mass is required. A linear momentum remaining constant over the conserved whenever the net force for zero or over specified period of time discussed above. Similar with the system, constant mass particles are rigid bodies. Net external forces acting on the system zero. The total sum of the individual linear moment vectors for all members within the system must remain constant. Conserve the force logarithm of force system is equal to zero. Linear moment system equal to constant linear. The system for the mass is mass 1, mass 2, the mass n. Mass amount of number for conservation linear moment that requires linear moment is conserved, which is net external is zero. Mass velocity 1 equal to mass velocity 2 times mass velocity 2, mass 2 velocity 2 equal to mass sequented mass number times mass to the nth to the vector nth and equals constant. Prime notation of velocity is also is in the above equation. Single later time condition. Note that the logarithm of force system is equal to zero. Linear moment must be conserved in all directions. Such equations may be written in particular directions, such as the y direction as follows, and equation similar to the one given on as follows, but the later solving impact collision problems in which elasticity colliding objects must also be given in solving the problems involved with the conservation of linear motion principle. Imperative to pay the close attention to sign conventions of all scalar velocities. Or impulse momentum principle. Impulse vector represented with the symbol IMP, defined as the equation impulse of 1 to the resultant second is equal to the derivative of the time square, derivative 1 or derivative L, force time distance, where Ft the impulse force acting upon the rigid body particle during the time period of time 1 greater than or equal to the time in time 2. For a constant mass object impulse equal to change of linear motion according to the equation, impulse is 1 to 2 equals mass times velocity squared minus velocity 1, or v velocity 2 minus velocity 1. For impulsive forces acting upon the object of the constant during specified, the forces of time 2 minus time 1 equal to mass times velocity 2 minus velocity 1. Scalar impulse motion equations may be written in any direction, such as the acceleration form of the constant mass time invariant impulse equals force x equal to time 2 minus time 1 equals mass times velocity 2x minus velocity 1x unit impulse of pound foot section Newton seconds. Caution: most be exercised converting in term units for the foot, pound meter foot seconds, or pound kilogram meter seconds. Recall the positive impulse force result in increased momentum, whereas negative impulse forces directed to opposite object initial velocity cause reduction in momentum. Impulse momentum problems in fundamental engineering exam often test for the impulse time period range required for a given force produce known velocity change vector triangle solution methods useful to avoid setting tedious scalar equations. Then it goes into a problem, example, and a problem. Alright, impact. An impact is a collision of two or more rigid bodies in which forces of collisions are equal and opposite of Newton's reaction principle. The external force acting upon the system is taken zero. Discuss preceding section. Total linear moment of the system and the colliding bodies must be conserved in all directions. Elasticity of the material constitutive of the colliding objects over the dramatic effect of the velocity of each of the immediate impact coefficients result restitution of is an important parameter for the solution of the impact problems of the defined. The coefficient of restitution 0 is greater than or equal to the coefficient restitution greater than or equal to 1.0, where the coefficient restitution it represents 0 of the perfectly plastic impact objects joint together after collision. Coefficient restitution is 1.0, represents perfect elasticity impact of objects, experiencing no permanent deformation. Energy is conserved. Typically, impact problems of the fundamental engineering exam involve one of the following situations: direct central impact head-on collision in which lines of action and the initial velocity become collisions that are collinear with joining on the center of mass. Oblique collision off-center in which the initial velocities have the components that are both parallel perpendicular to the line joining the mass center. Fundamental engineering impact problems usually active at the post-collision velocity, each for the object based on the given value of the restitution velocity before and after known of the object of the value of the restitution. That may be called from the direct central impact involved with the two objects and have the mass 1 and mass 2 with the following key object equations applicable to the primary. Note with the condition immediately after impact: mass 1 velocity 1 plus mass 2 velocity 2 equals mass 1 velocity 1 plus mass 2 velocity 2. Velocity 2 minus velocity 1 equals restitution times velocity 1 minus 2. Oblique collisions employ a set of equations similar to the above, except the velocities must be components along with the line of impact. Nth direction is perpendicular to the tangential plane of the impact. And that goes into angular momentum. Is a vector specified by age, defined by the moment of momentum for the constant mass object that has position velocity vectors r and v, respect of the reference origin O. Shown in Figure 8-9, angular momentum is given as a constant cross product as angular momentum is equal to vectors r and then x and the mass velocity. For fundamental engineering relating to angular momentum, r and mv are a two-dimensional plane with the direction of the angular momentum and necessarily a normal plane according to the right-hand rule for cross products. Magnitude of angular momentum is calculated using the angle between radius and angular momentum between r and m vectors and or objects angular vectors. Units angular momentum are pound meter foot squared second or kilogram meter squared second. It's important to recall that the net moment torque acting upon fixed mass object related to the rate of change angular momentum. The logarithm of momentum is equal to angular momentum circular arc type motion radius is equal to and magnitude applied with the momentum is related to the object angular acceleration according to the equation. Angular momentum is equal to mass radiant squared times angle. Against cam lobes by springs and distance pins of the pivot pin A given with the equation radius 100 cosine 30 plus 250, where R is measured in millimeters to determine the angular momentum of the pin pivoted after 4 seconds of motion. Initial angle with 0 is assumed 0 with the pin mass of 3/10 of a kilogram. Goes into a solution. Central force, motion, conservation, angular momentum. Motion, fixed mass object with the particle plane with the representative of the preceding section, and central forces that define external forces whose line of action always collinear with that position vector. Essentially, central forces used in the continual directed toward or away from the object's reference origin produce no net momentum or zero torque. Central forces, cable tension with the gravitational forces, concerning elastic forces, referring to equation 837. Momentum, angular momentum equals angular momentum change. Central force motion requires angular momentum remain constant. B. Conserve the following equation summary of the addition of the conservation angular momentum. Logarithm of momentum is equal to 0. The result in the angular momentum equals 0, and angular momentum equal constant. Magnitude angular momentum is also called angular motion over the mass radius squared times constant. And clearly, object angular velocity increases substantially when the distant object from the reference origin spin axis is reduced. Alright, 83, work energy. Work energy, the problem with the constant with a significant percentage of the total problem with the dynamic section of fundamental energy. Therefore, carefully review the concept of the principal work with the kinetic energy, principal potential energy, kinetic friction, conservation energy that is strongly recommended. Work of force. Of the force particle of the rigid body dynamics, work W is a scalar quantity with a dot product with an external force and net force displacement vector of the object particle. The governing equation for the typical mechanical work over the work is equal to the derivative of the force time of the distance time of the rate. The unit work is the foot-pound with a Newton over the meter over the joules of the rectangular plane motion represented the majority of fundamental engineering problems related to work energy equations listed below. Useful single force, net force component along with the line of action displacement cause work equals force x times the resultant of the x, where x is the displacement along with the x direction. Work force force y is equal to the displacement along the y direction. Work force F along the inclined direction. Positive work occurs when applied force, net force component same direction. If the displacement negative, work result of the net force of the direction opposite of the displacement direction. Additional, bear in mind when the force components over the force of the perpendicular of the displacement direction produce zero work. For covariant linear motion, work due to the force net force is given in equation 839. However, numerical calculations sometimes tedious but not often required in the fundamental exam. Usually it's advisable to employ principle of the work and kinetic energy discussed next is determine work done in a along curved path. Alright, kinetic energy. Kinetic energy is the energy associated with the object's mass at instantaneous speed v, and m, standard abbreviation K, utilizes the reference for the kinetic energy section beyond. Like all other energy terms, kinetic energy is scalar. Define following equation for constant mass object rigid body. Kinetic energy is equal to 1/2 times the mass times the velocity. Note the IP systems imputing values of the mass, pounds, mass, and speed in foot and seconds into the kinetic energy of the equation will not directly yield foot-pound results. Your ability to apply correct conversion will influence the degree of success of identifying the correct answer. Kinetic energy related problems such as the SI system, kilograms of the standard institute system, even the kilograms mass over the seconds, the mass over the speed of the term of the kinetic energy equation will directly produce quantitative results of joules or newtons in mass. Kinetic energy fixed mass object that can change only with a non-zero force or systems of force applied with the cause acceleration, deceleration, distance, net required for the work done over the object. Have the constant kinetic energy also be zero with the later with the section as shown with the amount of the kinetic energy possessed by a rigid body directly dependent on the objectional potential energy for the conservative of the process involved with the only frictionless forces. Potential energy is categorized in two major areas: gravitational potential energy associated with the object's elevation with respect to the reference datum. Ballistic potential energy is the energy stored in the compressed stretch spring, with the second and focus on the gravitational potential energy. Linear springs relieved of the next section. Of the potential energy with the due to the potential energy, gravitational potential with the due to the object's evaluation height with respect to the datum defined as follow. The potential energy with the work over the height with the equal to mass grams height of the work. W is the weight with the gravitational force of the object. With G is the acceleration of gravity, environmental weight, and to be measured gravitational work. WG is work due to the gravitational force of given the vertical displacement or elevation of the resultant height. Later it will be shown in the frictionless process with the only gravitational force acts for the changing of the particle energy with the rigid body equal opposite of the change with the kinetic energy. Linear springs. From the equation, gravity work is equal to the work, the weight over the resultant H over the weight over the H1 minus H2 with the gravity work related with the potential energy charge. The weight the gravity is equal to the potential energy 1 minus potential energy 2. And the negative potential energy object experiences with the elevation, therefore with the positive potential energy change with the increase of the subject with the negative gravity work because of the force displacement opposite direction conversely elevation and potential energy is required with the gravity work positive shown in the previously in example 8.10. Linear springs if the constant stiffness of the K recall with the force due to the spring given them with a simple equation. Forces of spring is equal to negative kinetic times x. X represents the spring with deformation, which amount with the spring stretch over the compressed and natural undeformed position, direction, spring force attached, object opposite, stiff with the direction, deformation, stiffness constant, K with the measure with the typical with the newtons over the meter with the pounds or foot. Nonlinear example exists with the stiffness constant varies from the spring length with the automobile coil spring. Potential energy stored in linear spring with elastic material is due to the energy required to compress a stretch spring with the computed with the equation. Potential energy of spring is half that of the stiffness times the x squared. Spring work weight is equal to the related change potential energy determined in this equation. Spring work is the potential energy of spring 1 minus potential energy spring minus potential energy spring 2 half of the position of spring kinetic stiffness x1 squared minus x2 squared x1 2 significant initial final deformation respectively. Equation 846 is valid both for rectangular look and covariant motion. Assumes no heat distribution spring during compression extension. And note that the work done in the spring positive of the deformation decreases x2 is greater than less than x1. The spring is unloading potential energy. Alright, kinetic friction is a shearing force due to the sliding motion of the rigid body with respect to the contact computation kinetic energy simply. Involves determining the coefficient of the kinetic energy, the normal reaction force of the acting on the rigid body, the force over the stiffness of the equal to the coefficient of the kinetic friction time with the normal reaction force, the value of the coefficient of the kinetic friction usually lower than the static coefficients of the same surface of the object with contact. Important recognize that the direction of the kinetic force, friction force applied with the rigid body above the direction relative to the velocity of the body with respect to the constant surface plane. Most fundamental engineers problems relate with the kinetic friction involved with the rectilinear motion with the typical problem that require the normal reaction determined from an object with a horizontal inclined surface in order to calculate the force of the kinetic energy, again using effective feedback with diagrams highly advantageous to solve the problems incorporating kinetic friction. Fact of the kinetic friction can forces opposed with the velocity of the direction relative to the surface directly with the contact object will cause the deceleration, consequently decrease the object with the kinetic energy and the contacting surface stationary. Work done by kinetic friction forces with the negative relative to the surface of the contact because of the work opposed to the displacement of the direction object with the kinetic force works result. Heat dissipation body of the reason of the kinetic forces are referred to as non-conservative. Then it shows an example and a solution. or we get the principles of working kinetic energy. One of the most useful problems solved with the methodology of the dynamic section of the fundamental engineering's principle work with the kinetic energy. The principle is positive the network produced the increase of the kinetic energy derived for the Newton's second law will effectively state with the network done on with a rigid body equal the change of the kinetic energy for any process involving conservative, frictionless, non-conservative external forces acting on a single object from state 1 to state 2, converting equation as weight net, the positive weighted net is equal to the kinetic and resultant kinetic energy equal to kinetic energy 2 minus kinetic energy 1. Constant mass object with the work kinetic energy equation is written as work network energy with equal to mass velocity squared over 2 times mass velocity 1 squared over 2 equals mass over 2 equal times velocity 2 squared minus velocity 1 squared. Equation is valid with both linear and colinear equations. The curve of the kinetic energy velocity 2 is always greater than velocity 1 requires positive network where negative work will result with a decreased kinetic energy velocity. No, the caution is needed with regard to the conservation and converting kinetic energy values into the working foot-pounds, whereas in impulse units, the initial final velocity is known with the work made. IP unit integrated part EIP initial final velocity is known with the network computed directly without involving the force of displacement. The fundamental engineering problems related to work energy, however, necessary to determine the force and velocity of the kinetic area values, various stages of computation, illustrating example 813. Alright, banking angles. Frequently encountered with the fundamental engineering exam topic, the circular motion problem, the banking angle of the road with the curved tracks, or the angle of the road, and very important with the consideration of vehicle safety, highway, or public transportation design. Effective banking angle banking angle will respect with the horizontal plane minimum angle required to keep the vehicle traveling at a maximum rated speed. VM, the sliding outward, assuming the friction is eligible because of the icy other slippery road. Surface radius curvature of the R is section of the roadway is known only with the path of circular. Newton's second law with the laws for the analysis of the normal and vertical directions for yield with the banking equation. Maximum rated speed is equal to the gravitation of the radius curvature of the tangent angle. Equivalent to this angle is equal to tangent into the negative first over times velocity meters squared over the gravitational times the radial. Or zero angle is measured in degrees. Conservation of energy of the motion of the rigid body, which only conservative force of the frictionless acting with a network done with a body independent path travel that depends only on the initial final position. Gravity work, ideal spring work, with example the conservative process of the weights for the no friction energy law for the principal work for the kinetic energy equation. Equation 849 can be readily shown as gravity is only type work done particle with a rigid body chain with a kinetic energy body particle with the equal opposite of the chain with the potential energy. In essence, they require the object subject to the gravity force. Example, the kinetic energy increases from state 1 to state 2, but the mass velocity of the potential energy amount equal to the kinetic energy rises between some two states. Energy is simply converted from one form to another. No energy is lost in the object of the surrounding environment. The conservation energy equation is given below. Equation 851 indicates the sum of the potential kinetic energy possessed by an object is constant for all states if only conservative frictionless forces are applied. Conservation energy requires frictionless properties. Kinetic energy 1 times potential energy 1 plus kinetic energy 1 plus potential energy 1 equals kinetic energy 2 plus potential energy 2 equals sequented to the kinetic energy number to the n to the plus potential energy to the n equals constant. Potential resultant kinetic energy equals negative resultant potential energy. Half the mass velocity 1 squared plus mass times grams times what is H? I forgot what H is. The drop is equal to velocity 2 minus velocity 1 squared, velocity 2 squared minus velocity 1 squared over 2. With the reference equation 851, many of the fundamental engineering dynamic problems with a rigid body initially with the rest of the velocity velocity 1 at 0, experience of elevation would drop at h1 to h2. The final velocity 2 with the lower of elevation h2 is given assuming no friction over the quad by the equation. Velocity 2 is equal to square root of 2 times the 2 times the gravity times the height. 1 minus height 2. Note that the free fall gravity motion without air friction equation is often used to calculate terminal velocity. Alright, 8-4, rigid body motion and plane. Motion, rigid body, two-dimensional plane, commonly attached to the top of the fundamental engineering dynamics. Says, section, typical problems involving rolling cylinder wheels, rods, perpendicular slots, gears, rotating 3D body, so on. Center of gravity, rigid body being analyzed, important parameters, solution, numerous rigid body dynamic problems, terms evaluated as CG, which we denoted with subscript C in this section. The following ones: the fundamental modes of the motion with a rigid body proven in plane with a transitional and rotational motion. Transitional motion, effectively rectilinear motion, displacement center of the gravity governed by Newton's second law, logarithm of force and mass angle of center of gravity. Rotational motion, spin body about the axis of the normal, path of the center of gravity, partial axis discussed on page 218. Magnitude rotational measured along familiar terms: angular velocity, angular acceleration. Applied torque of the net moment of the plane rigid body motion typically required measured respect of the center of gravity may be determined by using the following equation. New net momentum is applied with the commonly referred to as torque. Logarithm momentum center of gravity is equal to the inherent center of gravity angle, and IC equals mass moment of the narrative with the elevated with a particular axis to pass through the center of gravity. The object important concept of the mass moment of the narrative is reviewed in the next section. Okay. Mass moment of the narrow, mass moment of the narrow is the three-dimensional rigid body essentially measured with the resistance of the body, angular acceleration for any of the rigid body with one illustrated in the figure 818. Mass moment of the narrow, theoretically defined as the second moment of the mass. All mass elements of the distance of mass integrated through the entire mass of m over the body. An area is equal to the derivative of the mass times the radius squared times the distance times the mass, and where the representative of the momentum area to distance from any of the mass element axis of the inherent momentum beginning elevated. Recall that the units mass momentum conventionally kilograms times mass squared meters squared equals pounds meters times feet squared, and clearly performing above the integration of the where we at. Mass of the Teddy is staff. Therefore, equation mass moments in the air various familiar shapes, cones, spheres, rectangular plates, discs, and so on, provided in Table 8.1. Quick reference to the Fundamental Engineering Review pamphlet also contained the reference material of the inerrant momentum. Important to recognize that given the rigid body geometry, the formulas for the inerrant mass are directly dependent on the specific axis evaluating the inerrant mass. The x-axis is usually chosen perpendicular to the plane in which the force is acting on the body. For the inerrant z is evaluated the force combined with the x and y plane. Since the mass m object required to compute numerical value of the inerrant mass, product object's density values must be calculated to obtain mass not directly given in the fundamental engineering problem. For composite bodies and shapes such as cylindrical shapes, shaft connected with a circular plate disc. At the end of each composite mass moment in the narrow, given the axis of the algebraic sum of the individual moments for the narrow component shapes about the same axis components will usually require use of the parallel axis theorem, which is reviewed in the next section. Parallel axis theorem. Whenever the mass of the inerrant evaluated the axis body does not pass directly through the center of gravity or rigid body, but is required a parallel axis pass for the alternative location on the body, key equation for using fundamental engineering is the mass of moment inerrant specified parallel axis equals mass moment of center of gravity times mass times the perpendicular distance of the center of gravity to the point of parallel axis squared. Radius of gyration, rigid body with a mass, perpendicular distance k, the axis motion of the center of gravity point of the entire mass m, can be concentrated to produce the same moment with the inerrant gyration, original body with the center of gravity axis, one inerrant momentum, body of particular shape is obtained by the using table 8.1 radius gyration, radially computed relationship, inerrant momentum of the mass times the perpendicular distance squared, then radius gyration is resultant of perpendicular distance equal to the square root of the inerrant momentum over the mass. Rotation of the rigid body. Rotation of rigid body, the two-dimensional plane with a fix of the axis of the root of the point, with not necessary with the center of gravity of the body over the topic frequently presented with fundamental engineering. Figure 8.20 show the rigid body rotation of the xy plane and axis is passing through the point A, which is located with the distance r over the center of gravity of the body. Constant net moment is applied with the body will experience with the constant angular acceleration according to the equation. The above torque in the direction Z direction normal XY moment in the narrow with the Z axis of the axis of the rotation through the point A obtained with the even parallel axiom theorem, parallel in linear angular moment is equal to angular center of gravity times mass times radius squared. Since the motion of the center of the gravity circular motion point A, acceleration center of gravity with respect to point A may be to determine the tangential normal acceleration equations. Net force acting upon rotating body x, y, and x and y directions readily obtained. Angle of center of gravity x is equal to rotational work weighted square work equal to weighted squared times the result in the force of x equal to the mass times the radius times the w squared. I can't remember that. A central gravity y is equal to r radius angle times a result in the force y with the mass radius times the angle. Since the net momentum with the shown above, assuming the constant necessary for the angular acceleration a is constant, angular velocity w changes at the constant rate of the value of the angular velocity of the time, therefore is given as angular velocity time is equal to the angular velocity times the acceleration is constant times time, where the work with the angular velocity is a0 is initial angular velocity t is equal to 0, angular velocity expressed in radians and seconds, velocity constant, gravity around the axis entirely tangential determined using velocity center of gravity is equal to radius times angular acceleration and constant. Or velocity acceleration absolute relative motion, rigid body motion, plane with it can be described at the time of the tennis process, translation, rotation, many of the object, automobile, waves, conveyor belts, spinning baseball with exhibited type of motion. The fundamental engineering usually feature for the least one with a problem to catch over the understanding of the relative of the motion, 2 more points of rotating and translating rigid body, the advantage for developing with a proper solution of various problems. Figure 821.8 translating plane with the absolute velocity of the velocity of the A is shown on is considered the instantaneous center of the rotation of the body with all other points body of the common angular velocity W perpendicular axis of the axis through A. Plane A is arbitrary through point B that can be shown on the body with the necessary of the circular motion viewed at plane A relative to the velocity of the B respects the point plane A is denoted the vector point B over plane A with the magnitude velocity relative velocity calculated product straight distance radius equal to point B over the angular point plane A with the angular velocity is angular velocity of the point B over the angle A versus equals radius equals point B over the angular velocity. Relative velocity is combined within the absolute translation of the velocity A that produce absolute velocity vector B at V. Velocity vector at B is equal to velocity A and plus velocity B over A. The magnitude of the direction of velocity B is determined in the solution vector triangle illustrated in figure 822 using the law of cosines. For absolute relative acceleration, 2 rigid bodies experience translation rotational planes described above with equation similar to U for the relative velocity employed with the points A and B with the assumption A is given in the center of rotation. Angle A is at point B, angle A acceleration A at B, acceleration in plane A plus acceleration point B over plane A. Absolute acceleration vector A is shown in relative acceleration vector acceleration B over A determined with the tangential normal of acceleration components radius B over A acceleration radius B over A angular velocity respectively. The vector triangle that is constructed to solve the absolute acceleration at B. Methods useful in solving the absolute acceleration at point B. Circumference rolling wheel translation and accelerating central over the wheel of the point A given along with the angular velocity and the acceleration. Commonly used tests application relatively plane motion fundamental engineering. Rolling motion rigid bodies in plane rolling motion circular wheel or disc along horizontal plane surface is quite commonly encountered on fundamental engineering, and figure 823 illustrates the disc radius having the center point C at point P located on the outer edge. So we have figure 822 absolute plane of motion translation rotation about the axis of point A. To analyze the absolute relative of the motion of C and P with along the surface of the established with the tangential point of the contact between the disk and the horizontal plane with the absolute reference of the datum at any time of the angular velocity of the rolling disk given by the angular velocity using the counterclockwise rotation of the disk. The angular velocity expressed as angular velocity equals W times the stiffness from the rigid hand of the rule directly with the base of the previously established equation 8.1 through 8.17 plane circular motion, following a similar absolute relative of the motion center of the tangential P. Absolute velocity center C with the velocity center is equal to the radius of the angular velocity times the I. Note that C center move the tangential velocity with the negative x direction, have the radius of velocity, angular velocity L times relative velocity at point P with respect to the center. Velocity at P is equal to the sum of the angular velocity times the radius times the P over the angular center. Gravity spins P with a circular motion about the T at all time of the velocity vertical position illustrates the node with the relative of the velocity of the P in the specific motion shown as velocity P is over the center of gravity R over the angular velocity times J. Absolute velocity P with the varying position disk of the absolute velocity P with the vector sum of the velocity center gravity vector position P below over the center. Specifically velocity P is equal to volume center, velocity center plus velocity P over C equal to velocity center angular velocity of the radius in the point C over center of gravity. Absolute speed of the velocity P with the tangential point P is a scalar magnitude resultant with the velocity C and the velocity P over C. For position P is given in figure 8.23. We calculate velocity P as the radius of the radiant of the square root of radius r of the angular velocity squared plus r w radian squared, or 2 the square root of radius w angular velocity. Okay, moving right along here. 8.5 vibrations. Mechanical vibration problems involve the linear spring of mass frequently include with the fundamental engineering problems typical involving the spring degree of freedom of the system oscillate along the single direction rectangular motion following the second of the free damped transitional vibration similar with the key components equation symbol the problem of equations applicant vibrations and the consider relevant to the fundamental engineering. Example of mathematical derivatives involved with the solution numerously ordinarily differential equations bypass order to focus on the interpretation of initial conditions and physical parameters involved with the vibration problems. So the concentration should enable to identify readily and appropriate in use of the equations allow with efficient, accurate solution methodologies. Free vibration, type of the motion, and the character of the oscillation curve of the leaf spring with a mass system with external force excitation of the system initially stretched beyond with a statistic of the equilibrium position release typical of free vibration problems. Part of the value of the initial displacement of deformation noted as x to the 8.0 requires solution for the amplitude velocity period with the national frequency given the time and position, key parameter of free vibration presented with these symbols units given in the spring constant xk or the pounds and inches, new meter velocity x and second inches and second and foot seconds, millimeters seconds, etc. Mass objects, mass over the pound, kilogram, etc. Natural circular frequencies, angular velocity n is equal to square root of kinetic over the matters of the radians in seconds, period of vibration time, and the period of vibration equal to 2 times pi times square root of mass over the k is in seconds. National frequency. The natural frequency is equal to 1 over to the period of vibrations equal to 2 times 1 over 2 times pi to the times the radiant of k and the m of the radians in seconds. Displacement over the equilibrium xt in a minute. Inches, millimeters, and feet in sec, etc. Amplitude vibration k is equal to the radiant of the x to x is point x0 to the squared plus x0 over angular velocity squared, and that be inches, millimeters, feet, etc. Governing equation displacement free vibration without presence of damping is equal to x cosine of the angular velocity t minus the angle where the or phase angle, where phase angle is calculated phase angle with the tangent to the negative first of the x0 over x0 to n times the angular velocity, damp vibrations, existence of very vicious forces acting upon an oscillating system representing the condition of the damp vibrations, of the simplicity of the damping of the force, regard of the effect of the damp, the result of the motion with the dash pot, with the hydraulic cylinder. Key damping terms, some of the units are listed. Damping constant of the SC, pounds and foot seconds of the Newton, second and meters. Critical damping constants, critical damping constant 2 times mass times the angular velocity of this condition, most rapid to dampen the damping factor is equal to the constant over constant center, where damping factor representing the critical damping of 1, frequency with the damp vibration, angular velocity with the angle of velocity n over the radiant over the 1 times the damping factor in radians and section squared. Damping force is equal to the damping constant times x to the pound foot pneumatic newtons, etc. Natural frequency damping system frequency is equal to the angular velocity over 2 times pi equals to 1 times the Newton over t. F is clearly the reciprocal of the damp period. Damp period. Logarithmic decrement. That one's a little hard. Dimensional quantities of the decrement represent the natural logarithm ratio of the two consecutive amplitude, the ratio of the damp and the amplitude time, and the amplitude of the time plus what was that? Period displacement or something. Torsional vibration problems view the basic principle of the type of the oscillatory motion involved with the rectangular plate physical disc initial angular displacement angle while attached to the cylindrical rod. Figure 826 show that the angular displacement of the rigid body generated the twisting moment of the torque within the rod accelerated according to logarithm of momentum of the stiffness of the damp vibrations period. Times the inherent point 0 at angle 0. Kr is the torsional stiffness of the rod, Newton radians, foot pounds. Kt is the square root of J, G over L. G is the shear modulus. J is a polar moment in the momentum. L is the length of the rod. I mass momentum in the inerrant oscillation body is inerrant 0. And angle, the resulting angular acceleration radians in seconds. Then it goes into figures. Alright, summary. Dynamic, did I read that page? Yes, I did. A6, dynamic study of the motion, particular rigidity of the body, force of the governing of the motion, the dynamic section, fundamental engineering testing. Students, problem solving primarily with the topic area of the electrical motion calls varying motion, linear momentum, Newton speeds, second law of the force of the acceleration, works energy, mechanical vibration. Says for the dynamic fundamental engineering section, essential for the study to keep the understanding of the kinetic particle, to be familiar with the both straight line and curved motion, 2-dimensional plane, various types of problems involving position, velocity, acceleration, Cartesian plane, C, K, X and Y, well as polar coordinates, radius, and angle, and Z, are to be expressed with the ability to construct an accurate free body diagram, represent all external forces that include proper coordinated system located at center of gravity or motion, is highly advantageous skill of generating correct solutions. Kinetics is another major topic represented in the dynamic section of fundamental engineering. Knowledge of the several conservation laws is highly beneficial, specifically the laws governing conservation of linear momentum and conservation energy from the base of the numerous types of the questions relating to the rigid body motion. Important, remember, at the collision or impacts between rigid bodies, a system that converts the linear motion and elasticity of the colliding bodies influence magnitude of the direction of motion immediately after the impact. Therefore, students understanding vectors, their related scalar components will be an important skill to generate an accurate result within the problems area as well as many other topic dynamics. And it goes into some problems. More problems. Chapter 9, Strength of Materials.